So in this video, we are going to be introduced to some derivative rules. So let's get started. And all of these rules actually come from that limit definition. I'm not going to derive them here, but everything goes back to this, taking the limit of the difference quotient as h goes to 0. But we saw in the last section how that can be a very involved and tedious process. So there's got to be an easier way, and there is an easier way is learning the derivative rules, which actually come from that difference quotient. So let's start by introducing 4 of those. The first one, if we want to take the derivative of a constant value, that derivative is going to be equal to 0. And it doesn't matter what the constant is. If I ask you what's the derivative of y equals 3, you would tell me that the derivative y prime would be equal to 0. So that would be the slope of the tangent line for that. Our second derivative rule is a power rule. If I want to take the derivative of a power x to the n, I bring the exponent down, I subtract 1 from the exponent. So if we wanted the derivative of x squared, we would bring the 2 down. So the derivative is, bring the 2 down, subtract 1 from the exponent. So my new exponent would be 1, and we would just say that's 2x. Our third one is a constant times the power function. So it's a constant multiple of the power function. So we could think about that as bringing that c, that constant value, out and taking the derivative of the power function. And that would be the same thing as c times that derivative, which would be n x to the n minus 1, which would be c times n times x to the n minus 1. So an example there, let's say we had 3x squared and we wanted to take the derivative. So we would keep the 3, bring the exponent down, subtract 1 from the exponent, and then simplify. So we would end up with 6x there. And then our fourth rule that we have for now is taking the derivative of a sum or difference of functions. And that rule says you can take the derivative of each one separately. So you can take the derivative of f of x, and then either add or subtract, depending on what's in the problem, the derivative of g of x, which would be equal to f prime of x plus g prime of x. So just a quick example there. If we had y is equal to 3x squared plus 7x, and we wanted to take the derivative, we could take the derivative of each term. So taking the derivative term-wise here, keep the 3, bring the exponent down, subtract 1 from the exponent. Same kind of thing here. There's an understood 1 as the exponent on x. So keep the 7, bring the 1 down, subtract 1 from the exponent. So our derivative here would be 6x plus 7. So what I want to do is just work through a few examples of using these derivative rules. So we'll start out with a few basic ones, and then we'll make it more fun. Directions are going to say find the derivative. Let's say we have y is equal to x to the 4th. So our derivative, we're going to bring the 4 down and subtract 1 from the exponent. So it's going to be 4x cubed. Let's say we have y equals 3 over x squared. So in this case, we're actually going to have to rewrite that before we try to take the derivative. So I'm going to bring that x squared term up, and when I do, it changes the exponent to a -2. So now if I take the derivative, I keep the 3, I bring the exponent down, and I subtract 1 from the exponent. -2 minus 1 gives us a -3 as a new exponent. And then you always want to simplify. This is going to be -6x to the -3. It's fine to leave negative exponents. Let's say we had y equals x plus 1 times x minus 7. So we don't have a product rule yet. We will develop one later in the next chapter. So for now, what we would have to do is FOIL. So we're going to have x squared minus 7x plus x is a minus 6x. And then minus 7. And then when we take the derivative, we're going to have 2x minus 6. So we would bring the exponent down, subtract 1 from the exponent, and then when we take the derivative of the -6x, keep the -6, bring the 1 down, subtract 1 from the exponent, and the derivative of -7 is 0. So that's how we get the 2x minus 6 there. So now we have y is equal to, let's do 2x squared plus the square root of x all over x. So you're going to have to rewrite this one as well. So here's what I see. I can split the numerator here and then simplify each of the terms. X square root of x is the same as x to the 1/2. So I'm going to have a 2x plus x to the -1/2. And then if I were to take the derivative, I'm going to do it term by term. First term, 2, keep the 2, bringing the exponent down, subtract 1 from the exponent. Same thing here. I'm going to bring that exponent down, and then I'm going to subtract 1 from the exponent. So my new exponent is -3/2. Clean it up. 2 times 1 times x to the 0. Remember, x to the 0 is just 1. So this becomes a 2 minus 1/2 x to the -3/2. So let's do another one. And this is where you may want to pause the video, try it on your own, and then come back. So if we were to take the derivative of this, we're going to keep the 3, bring the exponent down, subtract 1 from the exponent, keep the -2, bring the exponent down, subtract 1 from the exponent, then keep the 5, bring the exponent down, it's an understood 1, subtract 1 from the exponent, and then when we take the derivative of pi is just a number, so the derivative is going to be 0. So we're taking the derivative term by term here. So our final answer is 21x to the 6th minus 10x to the 4th plus 5. Let's do another one. So take a minute, pause the video, try it, come back. So with this one, if we want to take the derivative, we can split the numerator. You can always split a numerator, you can never split a denominator. And then we're going to rewrite that. So that's the same thing as 12x squared minus 4x to the negative 1 plus x to the negative 3. So now if we take the derivative, we're going to keep the 12, bring the exponent down, subtract 1 from the exponent, keep the negative 4, bring the exponent down, subtract 1 from the exponent, and then take the derivative of that last term, bring the exponent down, subtract 1 from the exponent, and then clean it up. So we're going to have 24x plus 4x to the negative 2 minus 3x to the negative 4. So there's our final answer. And let's do one more just for fun. Let's say we have this. So we need to rewrite. So this is x to the 1/2 minus x to the 1/3 divided by x to the 1/5. And we can split that numerator. And then we need to simplify. So if we take and use our exponent rules here, we're going to have 1/2 minus 1/5. We need to multiply this by 5 and this by 2 to get that common denominator. So we have 5/10 minus 2/10, which is a 3/10. And then we've got to do the same thing here. So we have 1/3 minus 1/5. Get that common denominator. So now we have 5/15 minus 3/15, and that gives us a 2/15. So now we can take the derivative. So to find the derivative, we're going to bring the exponent down, and then we're going to subtract 1 from the exponent. So we're going to have 3/10 minus 10 over 10, which is a negative 7 over 10. And then same thing here, keep the negative 1, bringing the exponent down, subtract 1 from the exponent. So 2/15 minus 15 over 15 is a negative 13 over 15. So there's our derivative. So let's look at one more type of problem. Now that we know how to find derivatives, we can use that to help us find some things. So let's consider the function f of x equals 6x minus x squared. And we want to find what f prime of x is, the slope of the graph at the graph at 2, what the equation of the tangent line would be at 2, and then where is the tangent line going to be horizontal. So we know what this graph looks like. This is a quadratic and it opens down. And I'm just going to draw a quick sketch here. So if we wanted x-intercepts, we would set this equal to 0. So we would have an x-intercept of 0 and an x-intercept of 6. We also know that the y-intercept is 0, so this graph does something like this. So just kind of a quick sketch of what that looks like. We could also pop that in the calculator and get a good idea as well. So let's find the derivative. So in this case, to take the derivative, we're going to take the derivative of each piece. The derivative of 6x is 6, bring the exponent down, subtract 1 from the exponent. Same thing here, you're going to keep that negative 1 in front, bring the exponent down, subtract 1 from the exponent. So our derivative is 6 minus 2x. In part B, they're asking us, what is the slope of the graph at 2? To find that slope, we're going to use the derivative. So if we were to substitute a 2 into the derivative, we're going to have 6 minus 2 times 2, which is 6 minus 4, which is 2. So that tells us what the slope of the tangent line is going to be. Now they're asking us for the equation of the tangent line. So I'm going to come down here. To find the equation of a line, you have to have a point and you have to have a slope. Now we know the slope is 2, and we have part of the point. We know the x value is going to be 2. We've just got to find y. And to find y, we're going to substitute 2 back into that original function. So we need to find f of 2. And if we plug 2 in, we'll have 6 times 2 minus 2 squared. Now it's going to give us an 8. So we have a point, we have a slope, we can use point slope form. So we're going to have y minus 8 equals 2 times x minus 2. And I'm going to solve this for y. So we're going to have 2x plus 4. So graphically, here's what's going on. We're going to graph that quadratic, 6x minus x squared, and then we're going to graph that tangent line on top of it. So then when I hit graph, let me do a standard window. So there's our quadratic, and you can see the quadratic goes through x equals 0 and x equals 6, x-intercepts. And then here's the value 2, and you can see how that tangent line is touching that graph at 2. X equals 2. And that's what a tangent line does, is it touches the graph at one specific point. And then in part D, they're asking us, where is the tangent line going to be horizontal? So if we think about what a horizontal line is. So horizontal lines are going to look like this, and they always have a slope of 0. And we know that the derivative gives a slope. So let's kind of put that information together. If we want to know where we're going to have a horizontal tangent line, then we can take the derivative and set it equal to 0. And anywhere we have a minimum or a maximum is always where we're going to have a horizontal tangent line. It's always going to happen at a minimum or a maximum on the graph. So in this case, we've got the derivative, which is 6 minus 2x, and we're going to set that derivative equal to 0. And we're going to get x equals 3 for that. So we have a horizontal tangent at x equals 3. And that makes sense if you go back to your graph over here. Because if we were to go to 3, 1, 2, 3, and we go up, you can see that's where the maximum happens for this graph, and that's where we would have to have that horizontal tangent line.